Hey there everyone, welcome back. So what I'll do in this video is kind of give you an overview of why objects roll down inclines, right? And by objects I mean any object that's like a ball or a hoop or anything that can roll, right? So boxes or blocks don't really roll, okay? So what we have here is, say, a ball. It could be a hoop, but for whatever purposes, it's a ball. It's of radius r. All right, so we can put that as that, right? And it's rolling down an incline, inclined to the horizontal by an angle of theta. Now, in this video, I won't specify any numerical values. Okay, so I'll purely get some equation at the end. And I'll take that equation and I'll show you the relationships between the linear acceleration of the ball and other various quantities like the moment of inertia, theta, and others. Okay, so we'll only look at the relationships between the values, but this should give you a good idea of the physics behind objects rolling down hills. Okay, so to do that, we need to reach back to chapter 6 and do a free body diagram analysis. Okay, so that means we're going to need to determine the forces on this ball. Okay, let's see. Well, there's always gravity. I'll put that like this, right? I'll make that a dotted line because we'll need to break up that force into its components. One component parallel to the incline, which will be this force, and one component perpendicular to the incline, which will be that force, okay? And again, you should know that that angle is theta there, okay? So these components, if this is mg, this will be mg cosine, since that's the component next to the angle, that's the one that touches. This will be mg sine of theta, right? Since that's the same as this vector, which is the opposite to the angle. There's the force of, actually, let me take that back and write each component in a different color, each axis. There. So that's mg sine. Let's do it that way. So now the force of the incline on the ball, right here, that's the normal force, right? And let's see. There's gravity, there's normal force. Because this object is rolling and not sliding, there is friction, right? Specifically static friction, okay? Not kinetic in this case. There is static friction creating the rolling, okay? I'll say that the gravitational force makes it actually move down the incline, but it's the static frictional force at the point of contact right here that makes it roll. Okay, so you should know from the book that the point of contact in the reference frame of the ball, that's not moving, right? Worded another way, at every instant in time, we have a point of contact that relative to the ball and the incline does not move, okay? So in other words, its speed, its instantaneous speed at this point is 0. The instantaneous speed of these balls' center of mass, we'll say, is v, right, that direction, and the instantaneous speed of a point on this point of the ball, directly opposite the point of contact, this has a magnitude of 2v, okay? That's in the chapter. So that means that there's a static frictional force at the point of contact, making it roll in the reference frame of the ball, right? So if you ignore the incline and just look at the ball, you'll see that the point up here is moving this direction. The point here is actually 0, but it would move this way, right? Friction is trying to move it back up the incline. So because of that, that is the direction of the force of friction, and I'll say it's the static friction, okay? I should mention that that's not the same as the maximum static frictional force in this case, okay? It's just static friction. And I believe those are the only forces, okay? So let's write out the equations now. So sum the forces in the x. Oh, we need to write axes. Well, if the ball is rolling down the incline, that means the acceleration of the ball, the linear acceleration, is down the incline, parallel to the incline. So let's put one of our axes in that same direction, right? And then we'll put the y direction perpendicular to that. So now our positive force is mg sine, and the negative is the static frictional force, right? And because it's accelerating down the incline, we have it equal to the net force of MA, okay? And that's positive, again, because it's in the same direction as what the acceleration is, okay? Making our lives a little easier. So the y direction, our positive force here is the normal force minus mg cosine. And since it's not moving off of or into the incline, that's equals 0. That equals 0. However, we can't simply solve for A, right? We can't straight away solve for A because this is not, right here, not equal to the maximum static frictional force, right? It's not quite equal to that. So we can't just say it's mu times Fn. We got to do something a little differently. Specifically, this ball is rotating, right? It's rotating that direction. So thus there's a torque causing that rotation. Do you see which of the forces I've drawn is causing the rotation? So we have a torque now. In the reference frame of the ball, there's really only one torque, right? And that's the torque from the static frictional force. So let's do this in another color. Maybe green? Let's try that. This light green? Maybe too light. We'll try the dark green. Okay, so the frictional force here is acting a distance of capital R. Right? In other words, the radius of that ball away from the rotational axis. Right? So what we have is, I'm going to redraw it down here. Something like this. This is now our radius vector, and the force is perpendicular to that. Perpendicular. So now our torque, let's see, that's always R cross F, right? Whatever R is, whatever F is, it's always R cross F. And the sum of the torques, the net torques, after we've added up all of the torques, the net is equal to I alpha, okay? So the magnitude of R is capital R. The magnitude of F is, well, we can just say frictional force, right? We can just put F for right now. And that's equal to the moment of inertia for a ball, right? I'm going to leave this as I because I'm solving this in general, whether this is a solid ball, whether if it's a hollow ball or a hollow sphere, or if it's a hoop. So I'll just leave that as I, and alpha is alpha, okay? By the way, rotation, that direction has omega and alpha in the same direction, okay? Now, we're trying to solve for A. Remember? The acceleration down the incline. Well, A, the linear acceleration, is also embedded in alpha. So we can actually put alpha in terms of A. Let me get some more room here. So remember that alpha is the linear acceleration over the radius. So this is simply I times A over R. Okay? And now we basically have two equations, this one, and two unknowns. The frictional force and A. Okay? So, tell you what, I'm going to solve the x equation for Fs, right, the frictional force, and plug that into the torque equation. So that means friction equals mg sine theta minus ma, right? Now I'm going to plug that into the torque equation, which is right here, and we get the following. Oh, I should have the same R's. Let's make that a capital R. There we go. Okay, so distributing the R, we can eventually solve for A, right? Combine like terms and solve for the acceleration. So let's see. Well, let's divide both sides by R. IA over R squared now. Bring in the MA term to the right side. Equals I. And I'm going to factor out the mass as well. Equals A. Now we can solve for a final expression for the acceleration of the ball. Okay, so we have mg sine of theta all over this weird denominator term. And this is it, right? And again, this is for the acceleration of the center of mass, right? Which means it's the moment of inertia about the center of mass. Okay, so let's take a look at what this equation means. So, what does the acceleration depend on? Well, if we increase the angle of this incline, you would think intuitively that the ball should accelerate faster, right? So when is sine maximum? When the angle is 90. Well, 90 is just a right angle. So if the ball was on there, it'd simply be a free fall example. Okay? So if you increase theta, sine of theta increases as well, closer and closer to 1, which increases acceleration, right? Let's say if you increase, say, the moment of inertia of this object, right? If it's a hoop, it should be, oh, well, let me check my notes. If it's a hoop, is it 1/2? If it's a hoop, it's 1 mr squared. So if this is a hoop, it's 1 times mr squared, which, if that's 1, okay, compare that to now a solid sphere. A solid sphere is 2/2 mr squared. So 1 compared to 2/5, 2/5 is smaller than 1. So if we decrease a number down here, we decrease the rate of acceleration, right? Meaning if we were to have 2/5 mr squared for the moment of inertia, that means that a solid object, right, a solid ball, like a snowball or whatever, would have a slower acceleration than a hoop, which has all of its mass out here, right? Because 2/5 is bigger than 1, and 2/5 is on the bottom, okay? So that matches our intuition. Does the radius even matter, right? The radius of this object? Well, the radius, r squared, in the I term, is embedded in I, right? It's always some coefficient times mr squared. Well, we're dividing by r squared. So whatever you have for I, the radius goes away. So that doesn't matter, right? So this equation should match our intuition in those respects, okay? So I'll say that the gravitational force makes it move at all, right? This is what makes it go down the incline. Specifically, it's this mg sine theta component, all right? And it's the friction, it's the frictional force that makes it rotate, right? And with these two effects combined together, that's why it rolls, all right? So with that, thanks for watching.